Good afternoon, everybody. So yesterday day before, on the Friday, when we were discussing about this magnetic ordering, the idea was to start an experimental session, and today we are going to do. So generally, the program which we use to analyze this magnetic structure is the full Prof, and you can get this program from this ILL web page. So if you do the Google like full Prof. So you'll get this program, and depending on your system, you can install it. Now let's see that you have some data of this neutron diffraction experiment. So first thing is, let's see the data, how it looks like. So here is the data where we recently solved the magnetic structure. So this data file in our case is in the XY format. So first we start this program. Let me start from the beginning. Full Prof suite, and then first job is to define our working directory. What we do is, so this is my working directory, and I define any of this PCR file as a working file. Now, first idea is to look at the data. So here I go in this run when plot R 2006 and file, open pattern file, and then let me plot this data at various temperature. So let me start 5K. So once you try to open this file, it asks the format of data. There are various formats to put this neutron diffraction data. Like you can have column of X, Y, and error. X means your true theta value, Y means your intensity, and third column is your sigma, means error. You can have free format where you define your starting angle, step, and the final angle. And then you have a column vector which defines the intensity. So, okay. So data in our case is in the XY format. So let's put this XY sigma. So this is the data at 5 Kelvin. Now let me plot 5. After 5 I have 50K. Then I have 100K. Then I have 120K. Then I have 140. 160. Let me plot slightly higher temperature data like 240 now. 260. So now you can see in this data that once you are below 120K or so, there is additional intensity in the neutron diffraction pattern. And now this additional intensity is coming on the fundamental nuclear reflection. So this gives a hint that magnetic structure is probably ferromagnetic or ferrimagnetic kind of magnetic structure. Now this wind plot R allows you to see the data in various formats. Yes, so there is no additional peak. All this intensity is coming up on the top of fundamental nuclear reflection, and there is no additional break peak which is appearing in the low temperature neutron diffraction data. Now this full Prof program allows you to see the data in various formats. So here, right now this data is intensity versus 2 theta. I can change this data format to D. It is going to ask me the wavelength. Let me start with the one file. Let's say 5K X space Q, and it will ask me the wavelength, and I know the wavelength of the measurement, that is 1.094. So if I put this wavelength, it can convert the data now in this Q, which is momentum transfer vector. If you want, you can convert this data in this D space also. So these are the various way to see this data. So there's an alternate technique in the neutron diffraction where we do the time of flight. There generally we try to see the data in the D spacing. Now you can plot in the Q and you can plot in this 2 theta. So now you know by seeing this neutron diffraction pattern that there is additional intensity at low temperature. Now how we find out that what is the magnetic structure or in what kind of magnetic ordering this compound is ordering. So let me first tell you what is this compound. So this compound is lithium nickel, lithium nickel 1.5. Let me see. Let me see exactly. So this is, I think let me use bold. So it is lithium nickel 0.5, manganese 1.5, O4. So this is the formula of this compound, and X-ray diffraction tells me that it orders in a cubic structure. Now our first job before we determine this magnetic structure is to refine our nuclear Bragg reflection data, means data when your sample is in the paramagnetic phase. So for this compound, magnetization measurement tells that magnetic ordering temperature is somewhere around 120 K. So let's go to some file where my temperature is somewhere around, let's say 150 or 160. So here there is a small intensity still popping up. So you can see 5K and 160K data, and now here I plotted data at, let's say, around 240K. So you can see here this 240K is looking similar to 160K, but at 5K I have additional intensity. Now I will start this data from, let's say, 160K. So we will try to refine this neutron diffraction pattern where my sample is in the paramagnetic phase. So then to refine this, the first idea is we have to make a PCR file. So I will start from this 0th point, that how you make a PCR file for neutron or X-ray diffraction. So to make this PCR file, what you do is you go in this and let's click on edit PCR. Okay, and I define file new. So now I am trying to make a new PCR file for the refinement of crystal structure. Now in general, I can put this. So this general is any comment. So let me put this neutron diffraction LINI 0.5 MN 1.5 O, so 4. Now you go to the second tab, which is pattern, and in pattern you have to add now pattern. So let me add this pattern, add. Now once I put this, I click on this add, I get all this 5 tab activated. First I have to put this data file and peak shape. So here first thing it asks about the format of the data file. As we have seen, our format is not this 2 theta step, 2 theta final. So our format is in the XY. So I click this XY sigma format. So our data is in the vertical column XY. I have to define now this data file. So let me define this data file, which is at, let's say 160K we are refining. So I have defined this 160K data file. Now second tab comes of the refinement / simulation. Now there are a couple of options here. This option, if you click it, it allows the refinement of X-ray diffraction data. If you click on the second option, then you can calculate the X-ray diffraction pattern from the structure model, which you can provide as input to this PCR file. So suppose you are recording X-ray diffraction pattern of some sample and you want to quickly check whether it has formed or not formed. So you can simulate this X-ray diffraction pattern by using this tab. The other tab is neutron constant wavelength, which is the case we are dealing it. And another in the same way is pattern calculation. So same way like X-ray, you can calculate the pattern as well as you can go in this refinement mode. The third option is for the neutron time of flight data, which we are not dealing right now. So once you do this time of flight kind of experiment, then you have to choose this option. So we have clicked on this because we want to refine the neutron diffraction data. Now we have to choose the wavelength. So in general, this wavelength tab, if you are in the X-ray, they automatically comes to like copper, cobalt, or what kind of characteristics X-rays you are using. But we are in the neutron, so I would like to put it as user defined. And I know in my experiment, my wavelength is 1.094 angstrom. So I put my wavelength 1.094. I do not have any lambda to contribution. I am putting it as 0. And this third thing is telling this intensity ratio between lambda 2 means second order contamination. Sorry, lambda 2 and lambda 1, which is there generally in the X-ray. Sometimes it is there in the neutron also. So in our case, this ratio of the intensity of I2 and I1 is 0. So let me make it 0. Then I go to third tab, which is pattern calculation. So it's a peak shape. Peak shape in our case is pseudo void. So I will select here pseudo void. My scattering variable in our experiment is, so this pseudo void is the peak shape, which is combination of Lorentzian and Gaussian function. Maybe I will write sometime the expression how it looks like, or you can see in this manual of the full prof what is it. And this scattering variable in our case is 2 theta. So I click here 2 theta. Now this range of this data, I think let's see it from, so we start from 5.57. I know my step is 0.05 and my theta last is somewhere, I think around 100. Sorry, this is, let me just go in the last. So 60.05. step is 0.05, and this is the range of calculation for this peak width, which I am putting 8, and this parameter is incident beam angle at the sample surface is 0. So now let me click it OK. So we have defined this data file peak shape. This 3 part we have finished now. Now next part is background type. So there are a couple of options for the background, like one can put this 6 coefficient polynomial, one can put 12 coefficient polynomial, or one can put this point by point background. So I am choosing it here, this background where there is a linear interpolation between a set of background points with refinable height. I will tell you how to obtain this background points from this neutron diffraction data file. So this is my background. Excluded region. Suppose while doing experiment, you have some contamination from something and you know the location of this contamination. Let's say suppose you have some aluminum peak by your CCR or by your sample container. So you can put this excluded region. So here, just to show you, I am putting an excluded region at low angle, let's say 0 to 5.5 I am putting. So it means while refining, the program will not take this part in the refinement. So this is reason is excluded region. Geometry is my, this first what is selected, this, and corrections I have none. Now let me put also this OK. This program allow you to put your own scattering function, means on your scattering length, but right now we are not going to do that. But if you wish, like suppose sometime you have some element where you want to put your own scattering length, then you can put by using this option. So now let me enter this phase. Now first I have to add the phase. So I added this phase. Name of the phase. Let's put it as this is nuclear phase, because we are trying to refine the neutron diffraction data in the paramagnetic phase. So this is nuclear phase. Now structure model, this is correct because we are trying to refine this structure part. Coefficient to calculate the weight percentage of the phase, that is automatic. Now we have to define this contribution to the phase pattern. So type of pattern is our neutron and constant wavelength. Peak shape we are using is pseudo-void again, and reflections are automatically generated from this space group symbol. Now let me put it OK. Now let's put this space group of your crystal structure. So here the space group is P43. There is some special way how this, because the space group has to be put, or if you do not remember this symbol, you can directly put the number. So let's see what is this space group number for this space group. For that you can go in this Google. एक मिनट बिलबाऊ का, there was some Google page which I opened in the starting. Can I see it? No, there's one more. Okay. So you have an option to put here the space group symbol, or you can put the space group number also. So for this, you can go on to this Bilbao crystallographic server, and let's put the Wyckoff position tab. And here it will ask you to tell this space group number, or you can choose it. So I choose it. So a space group is Control F P 43. This is 212. So either I put it this way, or I can put 212 number. Then ask it to generate this symmetry operation. After doing this, you can click it OK. So it means we have fulfilled the information about this phase in the PCR. Now let's go to the tab, which is the refinement tab. So here it is background. We will import the background in the next time. I will tell you how to do it. You have the instrumental parameter where 0 is kept 0. Let's keep it like this right now. And now this important part here is to put the information about the atoms. So in this case, we have the atoms which are situated at 5 Wyckoff position. So how to get this information about this Wyckoff parameters? So I go to this space group number in the Bilbao crystallographic server side, and I ask this Wyckoff position for the space group 212, and let me click. So you find in this website that you have the Wyckoff letter, there is side symmetry, and there is a multiplicity. So in this space group, this 24E is the general site. General site means X, Y, Z. It can take any value, and you have other sites where your atom can go. So now we have to fill the information about this atom in the PCR file. So let me start. We have 5 Wyckoff positions in this compound. So I have created these 5 rows. And let me start with this lithium 1. This is lithium, and you have to put it X, Y, and Z. So I have some starting value of X, Y, Z. Let's put it 0, 0, 0. And then there is some temperature factor. Right now we can start from the 0. We will try to refine it, and then you have to put this occupancy. Now in this compound, this nickel, manganese, and lithium. So, and you have two positions for oxygen 1 and oxygen 2. So lithium occupancy, let me write it down, then I will explain you how to get this. So this is 0.333. Let me put this information from this nickel 1. So this type is nickel again, and then XYZ 0.625, 0.625, 0.625. B, let's put it 0. And now by seeing this position, I can tell that this nickel, for which this XYZ is 0.625, 0.625, 0.625. So it means it should be, so if I do 5 by 8. What should I get? Just check it. Okay, so 5 by 8, 5 by 8, 5 by 8. Okay, let me put another manganese. So this is manganese 1, this is nickel 1, and so manganese goes at 0.125, 0.37685, 0.87315. B, right now we have put 0, and I will put the occupancy. So occupancy as per the XRD I am getting for this is 0.16667, and for this it is manganese 1 is 0.5, and there are two oxygens, which is O1 and O2. So this is Mn, this is oxygen, this is oxygen. Now oxygen positions, what I have from the XRD data is 0.38156, 38156, 38156, and the occupancy is now O2, let me put it 0.15092, 0.139, 0.12380, this part 0, this part 0. And this thermal factor, which is responsible for this Debye-Waller factor, I'm putting them right now isotropic, and then let me put it click OK. Let me just check it again. Now question comes how we define this occupancy. So occupancy depends on at which Wyckoff position your atom is going. So if your occupancy is 1, let's say in this case, by seeing this, I can tell very easily that for oxygen 2, as it is going on the general side, so the occupancy is 1. So how do you get the occupancies? You divide this 24 by 24. So it means the occupancy for this atom which goes at 24 E side is 1. Suppose you have some atom. So let me use the, so how do you define this occupancies? Is the general side. So the occupancy for the atom which goes on this side is 1. Now suppose there is another atom, let's say nickel or manganese. They go to another side. So suppose if it goes to some 4A, 4 side, which is 4B should be the side which is 0.625. So nickel is at 4B side. So to write this occupancy for the nickel, what I will do is, so uh, board now. Ah, okay. Okay. So it goes to 4 side, 4 of something. So then this occupancy for the nickel becomes 4 by 24, which is 1 by 6. It means 0.16667. Similarly, if the Wyckoff position for some of the atom is 8, I'm giving a very general thing, then this occupancy of that atom becomes like 8, 8 by 24, means 1 by 3. Suppose atom goes on the Wyckoff position 12, multiplicity of that Wyckoff position is 12, then the occupancy becomes 0.5. So this is how, while doing the refinement, we determine this occupancy. Now these are isotropic thermal factor. Let's leave those at the 0 right now. Now I have fixed this information about the atoms. Let me put the information about the profile. In the profile, what you have is the scale factor. What is the scale factor? So as I told you, your intensity, which is calculated while doing this ritual refinement, is multiplied by some constant scale factor. So if the scale factor and then multiplicity, structure factor square, Debye-Waller factor, and then Lorentz factor. So this is the scale factor by which your pattern is multiplied. And now this A, B, C, alpha, beta, gamma are your lattice constant of your sample, which generally you know from the XRD. For this sample, the information which I have is this lattice constant A is 0.1945. It's cubic, so it is same. Eight 8.1945. Now these three things, alpha, beta, gamma, are your alpha, beta, gamma of your sample. So it is cubic material. So these three values are 90, 90, 90. Now this UVW, these are the property of your instrument. So they are this instrument parameters which defines, it depends a little bit on your sample also. So this defines the full width at half maximum of your sample. So for this, so this values generally you can get from your instrument scientist. So this value of UVW I am going to put here right now is, so this is the value for our diffractometer at Dhruva 7913. These are refinable, so one can refine it. 415. Profile. This is minus 0.4, and this W is, let's leave it at 0.22. So this value I put 0.22, and then okay. Now this other parts are more detailed, and right now you can leave it at, there are some asymmetry parameter which we will see later on. So I think I have covered major part which is needed to refine your diffraction data. So let me put OK, and let me save this file. So let's put this file name as test. And now once you have saved this file, you can look at this by going to this view PCR file. So I can tell you what are the things here. If you work in this text mode, so the job type is the kind of job you want to do it, like you want to refine X-ray diffraction data or neutron diffraction data. This is your profile. These are the background points which I would like to put it now in this file. And then this is the wavelength of your diffractometer, lambda 1, lambda 2, and other major things are this is the theta minimum, means from where you started the experiment. This is the theta maximum, means maximum 2 theta point where you have collected the data. And these are the number of cycles on which you have to run this refinement. So generally we can put it something like 40 to 50 cycles. These are the value of background which are right now 0. So we have to put this background so that it takes this correct background into the account. Here in this flag you find NEX equal to 1. It means we have one excluded region. And this thing here where it is written that excluded region. So this is the region which will be excluded for this calculation. Now this is the number of refined parameters. So these are number of parameters which you want to refine to match your observed and calculated pattern. N8 is the number of atoms. So you can see it 1, 2, 3, 4, 5. So we have 5 atoms. This is X, Y, Z. So it means this position of the atoms. This is isotropic B factor, means isotropic Debye-Waller factor. And these are the occupancy of the atoms in your sample, which we recently discussed. This is the scale factor by which you have to multiply your calculated intensity to match it with the observed one. UVW are your instrumental parameters which define the broadening of your peak, and this A, B, C are the lattice parameters, and this last thing Prof1, Prof2, they are the parameters which are responsible for the preferred orientation. So it depends which kind of model you are using. Generally I use with this NOR1, and then if I use it Prof1, it means there is no preferred orientation. And these are the asymmetry parameters which define asymmetry of your low angle peaks. So I think these are the major parts in your full Prof refinement file. Now let me just check whether we have done correctly everything. So job type 1 tells you that it is constant wavelength neutron diffraction pattern, and it is refinement, it is not the simulation or calculation. Now we have to put this correct background. So let me put this, save this, reload this PCR file, and then let me close it right now. Then now we have to see this background. Okay. Now let's open this and let's copy this data file of 160K by the same name like our data file. So I put it, paste it here, and I also make it the same test. So test.dat is the PCR file, and test.pcr is PCR file. So idea is, let's see this data file first. So this format is XY sigma, and we open it. Now let's see what is the point by point background, and for that you go in the calculation, go here background, and then you enable this background. Come again, calculation, background, auto detection. So let's select those default values. So these are the background which this program has in the automation mode detected. And then what I do is I save this background. Let me put a background and let me put this today's date 16/11/2020. Now let's see how this background file looks like. So this is, and open with, let me see if there is some text editor here. Yeah. So you see here, this is the value of your 2 theta and these are the background value which this program has calculated. Now we have to put this background in our PCR file. What we do again is go here, go to edit PCR. Now we can play one more trick. We can select our PCR here directly like test.pcr. Then go to refinement tab and background. So right now we have background 0.0000. You can see it from here and then import from background file. And this is the file which we created some time back. Okay. And then let me save it. Now you can see here the value which were previously 0, they are not 0. So we have background corresponding to every 2 theta value which was determined automatically. I can close this. Now you can see your PCR file from here also. So this is your PCR file. I think we are almost ready now to start this run for the refinement of this crystal structure. So there are two modes to run this. One is in this auto mode where the program tries to do lot of things in automation mode. But for the beginner, it is always good to work in the manual mode, means by putting this automation to 0. Now we generally start with this scale factor. I put it as 11. So the second row here, which is there with this every parameters, if I have to refine that parameter, so I have to put some flag which ends with the 1. So 11 means if I write number of refined parameter 1, it will try to refine this scale factor. I can refine this 0. It means there is a, suppose in your experiment, if there is a constant 2 theta 0 shift, that part also we should refine. So I can refine this by 21. Sorry, now. This part is not saved. It looks like. So let me first save this. I save this now and then again open it. So it is saved. Then if I have to refine this 2 parameter, I put 2. So first it will refine this. So these are the 2 parameters which will be refined in this list square fitting. So generally you always keep this scale parameter in the refinement mode, and I can refine this ABC also as they are same. So they will be refined by this same code. So with this now we are ready. Let me save this. And there are two ways to run it. Either you go to edit PCR and then run it, or you can run from this where it is written run full prof R. Let me just check it again that my auto part is 0. I'm trying to refine these 3 parameters. Scale factor, 2 theta 0 and my latest parameter. So it is giving, there is some issue here. that it is calculating this zero intensity. I do not understand why it is doing like this. So let's go. Edit PCR pattern. Data file is correct. The format of data file we have is correct. Refinement is correct. Let me just check quickly why it is calculating now zero intensity at every place. Uh, so we have job is 1, NPR 5, NPH 1, 32 is background, number of background points, that is correct. Number of NX is 1. We are not defining any user specific parameter, so this is correct. This parameter, okay, 20, 40, symmetry limit, I can put, but let's not putting it here. Let's see from the edit PCR. Data file, we have all right. This file, we have all right. Pseudo white, that is okay. Background type is okay. Vision, okay. This is okay. This is okay. This record factor is no. Phases, nuclear phase. Okay. I think, let me just check it again. Wait. Okay. So, uh, let's just run it again. So here I am trying to refine only three parameters. Now, this is how your refined file looks. Now you have couple of options to refine these parameters. So I can refine this like I have fixed now. I am refining this A, B, C parameters as well as scale factor. I can refine this atomic position. So if you are in the auto mode, then if you write 1 to this flag, then these parameters will be refined. So if I write like 1 here, program will take care and this parameters will be refined. So you have chi-square, it is 1.47. I think this is how you proceed with this refinement. Uh, you can do this refinement in this way also, like you go to this part and then here also you can see what are the things you want to refinement by going the refinement tab. Background, if you want, you can refine all. So here now I have tried to refine all the background points. Oh, it is giving singular matrix. So it looks like went in some odd direction. let me check it again. So that's for time being, remove all this refinement of this background. So this parameters where there is an ending with 1, it will try to refine those parameters. Here I am now making them 0 so that these background points are not refined. Or if you want to do quickly, you can go in the edit PCR, load this file, and then the refinement background, you can say fix all. Okay, okay, I save this, and then let me see this. Now I have fixed my background, and let me, the things which are refined now is scale factor, A, B, C are your lattice parameters. So in this position, there are some fixed positions which are not refinable, and some are general position which can be refined. And this you can find from this uh, Bilbao crystallographic server website. Like in this PICO position list here, like the 4A, 4B, these sites are special sites, so there should be no refinement for these sites. But like suppose if atom goes to 8C, 12D, or 24E, this position you can refine. So it is not that you have to refine always all the positions. Now I fix it and then I ask it to refine. And then you can check it, ERF. So this is how your diffraction pattern looks like. You can improve this refinement further. Like suppose we can improve this. So what we see still in this refinement, some of this peak intensity are not very well fitted. So we can use this preferred orientation factor. So I can put it here now 1. It means it will try to refine this. Oh, it will not improve. So when you do the refinement, it is always better to keep one file as a backup up to the best point you have reached, because if you try to work on the same file, sometime you may lose your whole the day work. Uh, you can now I can try to fix, I can try to refine these UV parameters which determine the resolution, which are determined by the resolution of your machine. I think more or less now we have refined this nuclear part for this sun. I can improve it further, but I think for this purpose, this is more or less the sufficient. So after refining this nuclear part, our next job is to go for the magnetic structure refinement. And the first step in the determination of the magnetic structure is to find out this propagation vector of the magnetic ordering. And now if you see this pattern, so so we know that we have no additional intensity up to 140 K, and I go to the base temperature. So there is enhancement in the intensity. Now I take the difference between 5K and 140K. So you go in the calculation, difference. So this minus 6. So you clearly see it that where this is due to this lattice parameter fluctuation, that there is an enhancement in the intensity at least at this 4 Q locations. Now we have to find out this K vector for this additional peaks. So what you can do is, this case is simple because you know that these peaks are on the top of nuclear reflection. So this K has to be 0, 0, 0. But we can do it here. So what we know is these are the 4 peaks where we have additional reflections, additional intensity. So I do it file reset PRF. So let me go to base temperature file. Sorry, file open data file 5K. So we know this enhancement in the intensity is 1, 2, 3, 4 peaks. Now what we can ask this program for this calculation, so there is an option here now to calculate this K vector. Peak detection, enable, save peak. Okay. So let me reset it. Let's go to PRF file which we made it. Now we go to calculation, peak detection and enable. Now peak detection, let's put the insert peak by hand. It's better to click it. This way gives the advantage because now here you have already taken care of this 2 theta 0. So let me, this was the first peak where we have this click here, third peak, this is the fourth. Calculation, this is now save peak as K search format. Now in the K search, it is taken this information from this PCR file that this is our lattice, means this is the space group. These are our lattice parameters. These are the standard format of this tolerance, and let's wavelength, it has taken 1.094, which was our wavelength. So let me just click it, and it is asking to run me. So you can see it has find out couple of solutions. And in this case, we can easily see that this solutions suits to us the best. So I think in the next lecture, we will start from this K vector and try to get this basis vector for the magnetic ordering and then try to understand how we can determine this magnet. Thank you. Now, if you have any question, you can ask me. If you have questions, clarification or some doubt, you can please raise your hand or type it. Okay. If you have question which comes in your mind later on, you can send your questions on the neutron lectures, neutron course at gmail.com. There's one more announcement that those who have not submitted their assignment of the basics of neutron scattering, they are requested to submit it in a week time or so now. So the next lecture will be day after tomorrow, means on Wednesday, 3 o'clock. So then we'll understand about this magnetic structure from this propagation vector. Okay.